These are your 4.1 notes on exponential functions. And chapter 4 has a lot to do with exponents, but we're going to start out with the graph and the family of functions. They're exponential just to get an idea of what the graph looks like and also use it to do some evaluating. One of the main things when we start talking about exponential functions to think about is what makes it exponential. What's the difference between it and the other family of functions that we've talked about in past chapters? Pop those up quick and have a look. So if we go chapters 1 and 2 where everything was linear, then chapter 3, our square, our quadratic, our root function, our absolute value function, and even circle. But what is different with all of these compared to this? What is it that makes it exponential? And it's pretty simple. If you look at all these equations, you notice that the x is like just down in our regular part of the equation. Where does the x sit here? It sits up in the exponent. And so what makes the function exponential is that your variable is the exponent. We have two types. We have a growth and decay model. The b is what we call our base. So look at our exponential function. We'll say what's the base, what's the number you're raising to the exponent. The a is a multiplier. That isn't quite as important as the base is. The base determines the type of function we're going to have. So if it's growth, we're going to say that base is a number bigger than 1. So 2, 3, 4, 5. Decay, if it's between 0 and 1, which means you got a fraction like a half, 2/3, 3/4. If you think about we'll talk about the graphs in a second, but if you think about it, you take a number like 2 and start raising it to larger and larger exponents, it gets bigger and bigger and it grows. On the other hand, if you take a fraction like a half, you start raising it to larger exponents, that fraction actually gets smaller, which causes a decay. And growth is the same idea as increasing, and decay the same idea as decreasing, another concept from past chapters. Okay, well the first thing we're going to do is get into the graphs. So we'll start talking about that, how they're generated, what are some of the unique characteristics, then we'll do some evaluating, and that'll basically most of the notes for 4.1. So for starters, I just want to get a quick visual of what is the difference between a growth model and a decay model. And the base is again the important thing, so this would be a base bigger than 1. And the idea is as you go left to right, increasing or growth. Here's a base between 0 and 1, so again like a fraction, 1/2, 2/3, 3/4, again something like that. And a decay would be a decrease, so decreasing as we go left to right. These two coordinates I have plotted in blue and red are also easy exponents to work with. So for example, this would be plugging in an x value of 0. One thing you guys would want to remember is that anything to the 0 power is 1. So that's what creates your y-intercept. And then if your exponent is exponent 1, then that'd be to the first power. So a 0 exponent and a 1 exponent are just easy, good choices. You don't need a lot of points to graph these. It's not like some of the other graphs that we do where we tend to do a few more points. Just those two will be plenty. It's more about growth and decay. Another unique kind of feature of a exponential function is it has what's called an asymptote. You might think of that as sort of like a boundary line. And I'll explain to you guys why that is, if that's there. The idea would be, and probably easier to talk about this one, for example, let's say I was using 1/2 and I did 1/2 to the first, so my x value is 1, that's 1/2. If my x value is 2, 1/2 squared is a fourth, then to the third, 1/2 to the third is an eighth, and so what's happening is the y values are getting smaller and smaller and smaller, but if you go a half, a fourth, an eighth, a 16th, and so on, you're getting smaller and smaller, closer to 0, but you don't actually get to 0, so you approach a 0, but you don't quite get there. So when you guys sketch, don't drop it down below the x-axis unless we shift this graph up or down, and then of course the graph will move, but so would the asymptote. We'll get to all that in a minute. So it's a boundary line, and it's just because of what's going on with the fractions. And when we do the graphs in a second, you'll see the numbers, you'll see how it's playing out. Okay, let's look at some graphs. First thing to do is just get an idea of growth and decay, and it's pretty simple as you guys scan down through the list of those red values, which are all your bases. Any base that's a number that's between 0 and 1 is going to be your automatic decay. So between 0 and 1.8 definitely fits in there. So that would be a decay. 2 definitely being bigger than a 1, so that'd be your growth model again. Very easy to figure this out. It takes about 2 seconds. 1.04 also being bigger than 1, so again we'd be with a growth. And then your last 1.5 obviously between 0 and 1, so a decay. Now what I'd like to do is have you guys kind of take a look at the graph. So we're going to talk about y-intercept, which is another question that's is part of this set of this part of the notes, excuse me. So if you think about the coordinate of a y-intercept, in any y-intercept the x value is always 0. So that means in all these places here where we have x's, we would want to put in a 0 to find our y-intercept. Now again, I mentioned just a second ago that anything to the 0 power is 1. So basically this becomes a 1 in all 4 of the problems, which means your y-intercept would be your a number out front. And again, let's have a look. So here's the first one. And again, 4.5 is my y-intercept because this becomes a 1. And that asymptote going on. So we're just going to kind of scan through and have a look. So just, the decreasing idea, there's a decay. Let's take a look at a growth. So here my y-intercept at 0.75, but again, growing because the base is bigger than 1. And just look at a couple more here quick. Another growth model. So again, because my base is bigger than 1, increasing or growth, and you get the idea, right? Okay, but it is good to have a visual right before you start, like what would I expect to see, especially if I'm going to draw it myself. Am I expecting a growth or decay? So you already know here's the graph should look like. And they're pretty simple graphs, pretty easy to work with. All right, just getting that basic growth and decay idea down like quickly, I can tell you what I have. Let's go do some graphing. So what we're going to ask you guys to do is generate coordinates to start, and then after a while we won't be doing a full table. Again, you'll have kind of a quick set of reference points you can use. But if we're going to use base 2, we're saying now take and raise 2 to all of these exponents. So when you're doing an exponential function, the x values in the table are actually what you're plugging in for your x. I want to pop those up for a second, and then we'll talk about how these numbers come about. So for example, let's take a look at how we get them. 2 to the 0 power, or anything to the 0 power is 1. 2 to the first is 2. Putting my exponent in right here, 2 squared is 4. And then these, we got to remember a little bit about how negative exponents work. So if you take a negative exponent, 2 to the negative 1, basically what we do is we put it as 1 over, or we drop that 2 down in a fraction. We call it a 1 over basically. And what that does is creates your 1/2. To negative 2 would be 1 over if I make the exponent positive, and 2 squared is 4, so there's your 1/4. So as a graph, let's check it out. Growth model, right? Because our base is bigger than 1. The 2 red points are these two, and again, if I'm just graphing a couple of coordinates, these are plenty. They're your easy exponents, I think. And then I just got to kind of remember again what's the style where my graph would be. Also, your y-intercept, picking that out. So that would always be created by your 0 exponent, because again, anything to 0 power is 1. So here's your y-intercept. And then asymptote, last thing. The asymptote, again, is something you should probably get in the habit of just sketching as part of your graph. So you're used to, hey, these graphs have a boundary line or some place where they don't cross. It's also good to think about why there is no graph down here. And the reason for that is to ask yourself kind of a simple question, right? 2 to what power would produce 0 or negative? And that is a question you cannot answer. So 2, you try to think of it 2 for a second. What exponent could I raise it to? Positive or negative or 0 that would produce 0. That's an impossibility. And also you can't raise 2 to any power and get a negative number, which is why there is a boundary line, and also why there's no graph sitting down here. So again, a little bit about just like what's true exponentially, what can we do? This cannot be done. Okay, so there's a growth. Let's look at a decay. And so we're going to switch over to 1/2. Now how I know it's a decay again is because that base is between 0 and 1. When I go to plug in, here's what's going to happen. So 0, again, will always produce your 1 because anything to 0 power is 1. 1/2 to the first, the 1/2. Squared, you would square the top and square the bottom, so there's your 4th. And then these negative exponents, you have to think about it as flipping the fraction actually is what makes this become positive. So if I flip that fraction over, it'd be 2 to the first. Flip that fraction over, 2 squared, and I get my 4 and 2. Graphically, you're talking about this, so there's your decay. Again, we got a y-intercept that would still revolve around that 0 coordinate, and then think of it as, again, asymptote. They're pretty simple graphs to do, so I don't think graph is going to be a big deal for you guys. It's just like remembering the style, which one's growth, which one's decay. And again, you don't need all of this, but at least those 2 basic points, the ones I have in red, are always your basic kind of starter points. All right, then of course we have shifting going on. So we did transformations in chapter 3, and you can shift any kind of graph. And so some familiar stuff coming back. We got our movements left, right, up, and down. One thing to do when you start looking at a function like this is just kind of remind yourself what's the parent. So the parent, like with no shifts, is 2 to the x. And that parent graph would look like this. There's 2 to the x, which we just did a minute ago. Transformations, quickly ask yourself, what are they? So we've got a right and we've got a down. And remember how that works. Again, it's sort of opposite when you're talking about attached to x. So right 4, down 3. And then basically all you got to do is take your 2 points and move them. Now also, because there's an asymptote, this would move along with the graph. So when you go down 3, this also goes down 3. And then again, it's just a matter of counting, right? So I'm going to go right 4, down 3, plot a point, right 4, down 3, plot a point. And then any up-down movement would move your asymptote along with the graph. So whenever you go up or down, basically if I'm starting here, just go right along with the graph. So like I said, fairly easy to graph. Okay, let's get out of graphing and try some other stuff. Some equation writing. So can you take the transformations and insert them? This one says you've got a translation of 2 units to the right and vertically 5 units down. So working off of our kind of base function. Again, the a value, that'd be a multiplier. That doesn't really happen here. But I try to figure out which movements do I have and attach them in there correctly. So remember that right is x minus 2 because you literally plug in the 2 and down -5. Again, fairly simple to do. All right, let's keep moving. You're going to do some basic evaluating with your calculator. This is kind of more just like knowing how to use my calculator than anything else, but plugging in an exponent and then crunching some numbers. So I'm doing the f of 4. Now we're kind of going back to function notation. So I mean f of, remember, plug in. So plug in 4, and then just evaluate on your calculator. I'll just do this quick for you guys. 4.5. So your calculators are all going to be different. I'm using a graphing calculator. You're using maybe more of a basic calculator, a scientific calculator. But it would go in pretty much the same. Most calculators have a set of parentheses. Here's my exponent key. You might have a y to the x key instead. And then I'm going to put in 4 and get my answer. I rounded a little bit, but there's the full answer. Okay, so this is just about getting around your calculator. I'm probably not going to spend much time here. Again, evaluate the functions. So plug in f of 8 and crunch the numbers on your calculator. All right, let's move it on. So we're going to come back around now to the idea of recursive and explicit rules. Haven't talked about those for a little bit, but this is the point where we start talking about a geometric explicit. The last time we did explicit, it was arithmetic, so we never did show you guys this way back in chapter, I guess that would have been chapter 1, because it was all linear ideas for the most part. This is really an explicit formula for an exponential, or geometric is how we talked about it last time, and basically do a little bit of quick evaluating. So if I want to do the f of, I'm going to plug in as my exponent. Now I put over here PEMDAS as kind of a reminder that when you go to do this, remember that you had to do the exponent in parentheses first. So I do 2 to the 0, which is 1, times 3 is 3. 2 to the first is 2, times 3 is 6. 2 squared is 4, times 3 is 12. So just remember your order of operations. And then when I go to do a recursive rule, this is actually explicit. Okay, so recursive, remember we always state, where do I start? What's my starter term? 3. And what am I doing? Well, basically I'm multiplying times 2. Here's a translation of what's going on. So here's my explicit. The A is like your use of 0, your starter. The B is the same as your common ratio. Remember some of those terms. So again, state your starter term, and then what's the rule? How are the terms generated? Now, working the other direction, this is recursive. So here's my starter, 16. 0.75 times the previous term. So there's my R. Here's my use of 0. So again, just getting used to the going back and forth between the two formats. Plug in use of 0, plug in R. There you go. And if I want to evaluate, basically I got to plug in 0, plug in 1, plug in 2. What's nice about explicit, if you remember, is that you can plug in whatever term you're trying to find. That's what you evaluate at. And recursively, this isn't that big a deal. I suppose we're only going 3 terms, but if it's recursive, you got to go 1 term at a time. If I want to go out to like the 10th term, I could plug in 10 explicitly. If I was going to do recursive, I'd have to do like 10 blanks to get out there. So explicit is always quicker, especially if you want to go way out. And then, of course, explicit is nice when we're doing word problems, which is kind of the last thing we're going to talk about. So a little flashback to recursive and explicit as a geometric format. And again, just getting used to how it's written. Pretty straightforward. Let's go look at the last little bit of this. So last thing we're going to do is do a word problem and use the explicit formula and talk about it recursively too. So depreciation, which means a decay idea. So we're losing value. Suppose you buy a car for $14,000 brand new. It depreciates by 1/5 of its value every year. So 1/5 is like 0.2 or 20%. So we're saying it's losing 20% of its value every year. So recursively, starter value, what the car was worth when I bought it. And remember this idea, it's not 20% that you're putting in here because we're talking about the value of the car. This is the car's loss in value. We're saying it still maintains 80%. So remember that idea of how you switch back and forth between the two. When you go to do explicit, basically we're just going to plop it into our explicit rule and have a look. So 14,000 being my starter, my use of 0, and R being 80%. And then again, all I got to do to evaluate it is just go ahead and plug in. So what's the F of 2.5? What's the car worth after 2.5 years? And again, it should be less. It's a decay model. So I should be down to less than what I started with. Okay, that's the end of the 4.1 notes, kicking off the chapter with exponential functions.